Good evening, everybody. First of all, I would like to thank to the third ICePTi committee member for giving me a chance to present a part of my research work here. The title of my talk today is Effect of Magnetic Field Direction on Mechanical Properties of Chitosan Membranes. Myself is Ninyoman Rupiasi, and one of my colleagues, Mr. Made Sumadiasa, and one of our student, Ida Wisnusari. We are coming from Department of Physics, Faculty of Mathematics and Natural Science, Udayana University, Bali. The contents of my talk today is introduction, materials and method, result and discussion, and finally conclusion. I start with the introduction. Chitosan is a biopolymer which composed of glucosamine and an acetylglucosamine unit linked by glucosidic bonds. Chitosan has attracted great interest due to biocompatibility, biodegradability, high charge density, non-toxicity, antibacterial effect, heavy metal absorption, film, and membranes. Here is some application for the chitosan. First is chitosan film for packaging, particularly as unedible packaging. Chitosan-based membrane used in reverse osmosis, gas separation, dialysis, and perforation. It is used as a composite, polyelectrolyte complex, or a blend with another polymer. In our previous study, we have made, characterized, and used chitosan membranes with various composition, mainly as wastewater treatment, such as we have made chitosan membrane as a filter for removing sulfur from X-ray film processing waste. We found that the chitosan membranes were able to filter sulfur from X-ray film processing waste. Also, we have used to study ion transport in various electrolyte solutions. We have also made chitosan composite membranes CH8G and P in order to improve the mechanical properties of chitosan membranes, and we have used them to filter sulfur waste from X-ray film processing waste. Also, we have tested for antibacterial activity. We found that the composite membrane will give a different result. The composite membrane is able to remove sulfur waste better than the pure chitosan membrane. Also, the composite membrane has more antibacterial activity compared than the pure chitosan membrane. The properties and the performance of those membranes also change depending on the method of making, the environment, and the operational condition. Some researchers also have reported that the properties and the performance of membranes are very depending on the method of making, the environment, and the operational condition. Based on this background, we made chitosan membrane under magnetic field condition by varying its duration and direction of the magnetic field. We hope this study can give structural information which is correlated with performance when analyzing membranes design for filtration purposes. The objective of this study is to evaluate the effect of magnetic field direction on mechanical properties of chitosan membranes. The study included thicknesses. The mechanical properties of the membranes includes ultimate tensile strength, elongation at breaks, and elasticity of the membranes. Also, we have studied about functional groups and then the X-ray diffraction. For material and methods. Material that we require for membrane preparation, such as Chitosan powder, that is shrimp-based product with degree of deacetylation 87.9%. Also, we use demineralized water for solution-based preparation, and then acetic acid 1% and also sodium hydroxide that we require during membrane preparation. For method of preparing the membrane and then delivering or preparing the magnetic field direction. The membrane was prepared by a casting method using Chitosan as a matrix and acetic acid 1% as a solvent. During membrane casting, a magnetic field of 1.5 millitesla in the direction of horizontal, or we can say parallel, or noted here by big H, and vertical or perpendicular, which noted by big V, is applied for 2 hours, 4 hours, 8 hours, and 12 hours. Simply, we just called as treated membranes. Also, we have prepared 2% Chitosan membrane without magnetic field that we call as a control or membrane control, namely M0. This is the protocol to prepare the Chitosan membranes. This is the membrane, the form of the membrane that we made. And then, for the magnetic field direction, we have designed the magnetic field in the direction of horizontal or parallel to the surface of the membrane, and also we have designed for the perpendicular direction of the membrane. For the magnetic field, we have designed a homogeneous magnetic field generation system in a particular room. It developed by using 4 Helmholtz coils, which radius of 15 cm and number of turns 130 turns that connected in parallel and coaxial. The both coils were fixed at the same distance as the radius of the coil in order to get a homogeneous magnetic field between the both coils. For the design, we got the homogeneous magnetic fields around -7 cm to positive centimeter between the both coils. The magnetic field used is 1.5 millitesla and the duration of the exposure is 2 to 12 hours. The diagram of the direction of the magnetic field on the membrane surface. This is the parallel direction or horizontal direction. This is the surface of the membrane, and then this perpendicular or vertical magnetic field that across the surface of the membrane. Characterization method. First, we measure the thickness of the membrane that we have made. Second, we have studied about the functional group by using FTIR spectrophotometer. Also, we have studied about the tensile test using dynamic mechanical analysis, DMA, and also we have studied about X-ray diffraction, XRD. We come to the result and discussion. First, thickness. Figure 1 shows the thickness of the membranes which get magnetic field during the casting process, that all the membranes or those treated membranes are thicker compared than the control one. we can see here the thickness of the membranes which treated with the parallel or the perpendicular magnetic field almost not much change or almost the same. See? As increasing the time of the magnet of the membrane uh, in the magnetic field condition, the thickness of the membranes increase, but after 12 hours, the thickness is decreasing compared than the other time. But the thickness is still greater or thickness more thick compared than the control one. For the functional group of the control and treated membranes, we also study and then we reported that all the peak that found in the control membrane also we found in the treated membrane, either treated by the parallel or perpendicular magnetic field direction. Only the peak slightly gets shifting to the smaller or larger wave number. There is no new peak found. For X-ray diffraction, the X-ray pattern of control Chitosan membrane show this one. So two characteristic peaks at 2 theta around. One is 15.91 degree, that is a crystal form 1 due to the to bond water molecule into the crystal lattice of Chitosan, which form hydrated crystalline structure of Chitosan that gives rise to a predominant polymorphism. And the second peak is at 2 theta around 22.57 degree. That is a crystal form 2 is the indication of the relatively regular crystal lattice 110 of the Chitosan. The magnetic field, either parallel and perpendicular treated membrane, exhibit that more oriented crystal structure, that is regular crystal lattice 110 of Chitosan. The first crystal form disappear. It means all the membranes which treated by magnetic field, either with the parallel direction or perpendicular direction, it will get oriented the crystal structure. It means only come to the second structure. The first structure disappear. So the same thing with the membrane which treated by the perpendicular magnetic field. Here we can see that also that one new peak, very sharp appear in the magnetic field treated by 12 hours with the magnetic field parallel in direction, but in the magnetic field perpendicular direction, this peaks already exist when the membrane just exposed only for 2 hours. But for the parallel treated, it requires 12 hours to bring this new peak. It means the direction of the magnetic field affected the crystal structure form of the Chitosan membrane. It is depending on the time and then the direction of the magnetic field given. If we look for the crystallinity of the membranes, the crystallinity of the treated membranes either with the parallel magnetic field or perpendicular magnetic field, the crystallinity is smaller compared than the control membrane, except for the membranes which treated with the 12 hours, either with the parallel or perpendicular magnetic field. We come to the tensile test. For the tensile test, this figure 5 showing the stress strain curve for control as well as for treated membrane. This is for the membranes which given by parallel magnetic field direction, and then this curve showing that the stress strain curve for the magnetic field which have given perpendicular magnetic field direction. Then if we look for the elasticity or the Young modulus of the membranes, we can see that the uh, the Young modulus of the treated membrane is smaller compared than the control one. It means the membranes is more elastic compared than the control one. But the value changes uh, in randomly. And also for the ultimate tensile strength and elongation at breaks, also generally the ultimate tensile strength and elongation at break for the treated membranes is bigger compared than the control one. For the uh, for the elongation at break, especially for the chitosan membranes which exposed by parallel magnetic field for the 2 hours has very big number, that is more than 35%. It means this membrane is very elastic. So we can say that the ultimate tensile strength and elongation at break of treated membrane are greater than the control one, I have already explained. And then the control membrane has highest elastic modulus, ultimate tensile strength, and elongation at break are the smallest. The highest ultimate tensile strength and the elongation at breaks are found at the membranes which exposed by a magnetic field in parallel direction for the 2 hours. Based on those results obtained, it can be concluded that first, the chitosan membranes which have been treated with magnetic field are thicker compared to the control membrane. The direction of the magnetic field has no effect on the thickness of the membrane. Second, the FTIR analysis showed the functional group which present in the control membrane were also found in the magnetic field treated membranes. The peaks slightly shifting to smaller or larger wave number. There is no new peak observed. The tensile test obtained that the control membrane has the highest elastic modulus among all membranes, while the ultimate tensile strength UTS and its elongation at break BE are the smallest. The highest ultimate tensile strength and the elongation at break was shown by the membrane which 2 hours exposed to the magnetic field, particularly in parallel direction. The magnetic field, either parallel or perpendicular treated membrane, exhibit a more oriented crystal structure that is the regular crystal lattice 110 of Chitosan. The first crystal form disappear. The crystallinity of the threaded membranes lower than the membrane control. But as increasing the time that magnetic field applied, the crystallinity of the threaded membrane increased, where on 12 hours the magnetic field of the threaded membranes is 45.9%, meanwhile the untreated or the control membrane is 43.7%. This result indicated that the mechanical properties of Chitosan membranes are affected by magnetic field direction, which is given during the formation state. It is improved the mechanical properties of the threaded membrane. Acknowledgement. This work was granted by the Ministry of Research, Technology and Higher Education, Republic of Indonesia, under Basic Research PDUPT grant of Udayana University, year budget 2021, and also by Udayana University funding are highly acknowledged. These some references that we have used during the study, and then finally we come to the thank you.